Okay. All right, so suppose that 700 feet of fencing are used to enclose a corral in the shape of a rectangle with a semicircle whose diameter is the side of the rectangle. You're given a diagram with variables, so that's nice. You don't have to make them up yourself. Find the dimensions of the corral with the maximum area. So our objective function is what? What quantity? Area, right. Total area enclosed. So my objective function is area. We'll call it A. The maximum area is what we want to do. Maximize the area. Okay, so there's two parts to the area. There's the area of the semicircle on top and the area of the rectangle beneath. So what's the area of this semicircle in here? Pi r squared over 2. Now we're given a variable x. It looks like we need to work it in terms of x. So how do we write r in terms of x? Yeah, the radius is half of that, so r is x over 2. Okay, so I'm going to write it out up here where I have more space. So the area of the semicircle is pi r squared over 2, but the radius is x over 2. So pi times x over 2 squared over 2. So that is the area of the semicircle. Okay, plus the area of the rectangle. That's much easier. Yeah, xy. Okay, but I need to get it all in terms of x or all in terms of y. So I have not used what fact yet? The constraint says we have 700 feet of fence. Okay, so how do I write that as an equation in terms of x and y? See, so my constraint is that the distance all the way around is 700, so I'm going to start here, right? So it's y plus x plus y, so 2y plus x plus half the circumference of the circle. Yes, equals 700. So here, so we've got y plus x plus y plus half the circumference of a circle equals 700. So that's 2y plus x. Those are the sides of the rectangle. This is not a fence right here, but this is. So semicircle, circumference of a circle is 2 pi r. So half of that would be pi r. But I don't want to use r. I want to stick with x and y. So r is equal to x over 2. And let's solve that for y. I don't want to really solve it for x because I've got this mess up here. I think it'll be simpler to plug in y right there. So let's solve this for y. Okay, so we've got 700 minus x minus pi over 2x equals 2y. So if we divide both sides by 2, 700 over 2 is 350 minus 1/2 x minus pi over 4x. And you could combine the x's if you want or leave them separate, either way. So I'm going to plug that into my objective function to get my objective function all in terms of x's. So my objective function becomes area is the area of the semicircle plus x times y. Okay, for the semicircle, let's simplify this messy looking expression as we go. Okay, this 2 I'm going to put under the pi, and I'm going to write it as pi over 2 times x over 2 all squared, and then I'll keep cleaning it up with each step. Okay. Plus x times y is x times all of that is y, so 350 minus 1/2 x minus pi over 4 times x. Are y'all following me so far? Okay, this y is right here, which I'm plugging in right here. Okay, so we're getting area all in terms of x, and that is it, but I think we should keep going and simplify a little bit more before we differentiate. Okay, just to make it easier. So this first term is kind of messy. If we square the x and we square this 2, what are we going to have down here? A 4. So we'll have pi over 2 times 4. That simplifies to pi over 8, all times x squared. And I like to write it like that with my constant out front, because when we differentiate, I don't want to be using the quotient rule and chain rule on this. I just want to get it where it's like a big constant times my variable to a power. That's much easier to differentiate than trying to use quotient or product and chain rule. That's not necessary. So keep simplifying until we differentiate. Here, let's distribute the x. So we'll have plus 350x minus 1/2 x squared minus pi over 4x squared. You could combine those two terms if you want, but this is not too bad to differentiate. That's pretty good. So let's mark this equation. Do y'all want to keep going with this or leave it here and you've got it from here? Keep going? Okay. So I think that's a pretty far simplified, oops, so this works, objective function. There we go. Okay, so we need to find critical values, right? Try to find where the area is at a minimum. So for the derivative of that, okay, pi over 8 times the derivative of x squared, we bring the 2 down, so we'll have pi over 4 times x to the first plus 350 minus 1/2 times 2x is 1x to the first minus pi over 2 x to the first, yes? So I'm getting, oh yeah, I could have combined these, pi over 8x squared minus pi over 4x squared. That would have been nice to combine, but I didn't even see it. That's okay. So the derivative is this. We want to find where does that equal 0. The only term without an x is this 350. So I'm going to move the 350 over to the right. And let's combine like terms. So pi over 4x minus pi over 2x combines to what? Pi over 4 minus pi over 2 is 2. Pi over 4 minus 2 pi over 4 is negative 1 pi over 4. So minus pi over 4x. That's just combining the first and last term there. Then we have this minus x equals negative 350. I put the wrong thing on the wrong side. Now everything's negative, so let's multiply both sides by negative 1. Everything becomes positive. And let's factor out an x. That's how you get x by itself. So if we factor out the x, we're left with positive pi over 4 plus 1. I made everything positive. So I get this. So we're almost done. So x is 350 over pi over 4 plus 1. And that is a critical value. It's probably going to be where area is maximized. Was that right? Yeah. Okay, we got everything in terms of x. So let's think about this for a minute. Going up here to this original function. If x is 0, I'm trying to figure out like endpoints. Or do we just use the second derivative test? Okay, so for the interval for x, if x was 0, what would the area be? Right, if x was 0, it would be like squished, right? So you wouldn't really have, I guess you would just have a fence and a fence. It wouldn't make any sense. So total area would be 0. What if y was instead 0? It was flat. It's a little complicated to figure out, isn't it? But I can pretty much tell from thinking about it that if y is 0, you're probably not at maximum area, right? Let's just use the second derivative test instead of trying to figure out that endpoint, because that's going to be a little bit challenging to figure out. You'd have to use the circumference of the circle and all that, which we could do, but instead I think it'll be easier to just find the second derivative of a, because I'm fairly confident that the area is not maximized if x is 0 or if y is 0. Yes?
Is it safe to do the second derivative every time? Is that okay?
No, I showed you that one example where it wouldn't have worked. Well, that's not true. I showed you the circle example where you would have gotten the wrong, like it wouldn't have been right with the second derivative test, and you would have had to go find the endpoints anyways. So yes, 95% of the time you can use the second derivative test. Yeah, and then if you don't get what you expect. Where's my, oh, here's A. That's what I'm going to differentiate. So the derivative of pi over 4x is pi over 4. Derivative of 350 is 0. Derivative of negative x is negative 1. Derivative of negative pi over 2x is negative pi over 2. It's actually constant. Is that going to be a positive or a negative number if you put it all together? Definitely a negative number, which tells us A is concave down. And so area does have a max up there at the top of that max because it's concave down. Okay, so A has a max at the critical value. So that we can just, you know, check. Okay, we checked. It's a max. What did the question ask for? Find the dimensions. Okay, so we've solved for x. That's x. Did it say to round? No, we're not rounding, are we? So that's the exact x, and then you could go back right here, plug in your x to get your y. I think y'all can do that. Did I answer whatever questions you had about this? Somewhere in there? Okay, what other ones do you want to look at? Huh? We did 10. 10. Have I done 10? Nope. Number 10. Okay. Okay, find the dimensions of a cylinder of volume 7 meters cubed of minimal cost if the top and bottom are made of material that costs twice as much as the material for the side. This is the kind of problem they do in business calculus. If you're wondering the difference, they do more stuff like this. Okay, a cylinder. We need a nice picture here of a cylinder. That's probably a little too big, but that's okay. Alright, so there's my base, there's my sides, and then here's my top. The dimensions, so it has a volume of 7, and we're trying to minimize what? Yes, find this minimal cost. So that's our objective function, is cost of the thing. We want to minimize cost. Okay, so cost is, let's see, the top and bottom are made of material that costs twice as much as material for the side. So the top and the bottom cost one amount, and then the sides cost a separate amount. So let's break it up into the sum. Cost of the top and bottom plus the cost of the sides, because we know they're different. Okay, we have a cylinder. Cost is, okay, like if you're building a giant cylinder, how do you compute cost? How do you compute cost to make the top, let's say? Yeah, how much material does it take to make the top? That's referring to area, right? So it's your area times your cost, whatever that is. Now it doesn't give us any dollar amounts. Like, so let's say the top and bottom cost $1 per square, per square meter. Then the side would cost what? $2 per square meter. And apparently it's not going to matter whether the cost is $1 and $2 or whether it's $2 and $4. It's going to work out, the problem's going to work out the same, right, to minimize cost. All we're given is that the cost of the top and bottom are twice as much as the material for the sides. So, but anyways, my point was that cost is your area, total cost is your area times cost per square foot or cost per square meter. Okay, so we're going to, for simple purposes, we're going to suppose that the cost of the top and bottom are $1. You don't have to put a number on it. You could give it a variable. I think it just adds to the complexity, though, unnecessarily. So we're going to suppose that the cost of the top and bottom are $1 per meter squared. So the cost of the sides is $2 per meter squared. Okay, so what formula do I use for the area of the top?
The top and bottom should be more expensive than the sides.
Oh, did I do it backwards? Thank you, I did. 1 and 2. See, thanks. Okay. Yeah, top and bottom is twice as much as the side, so that makes more sense. Good. Okay, so the area of the top and the bottom is the area of a circle, which pretty much right there tells us what our variable should be. What should I use as a variable here? Area of a circle is pi r squared, so let's use r. Yeah. I don't know. It says find the dimensions. That's what I'm trying to find. So when it says find the dimensions, that means we want the radius of the cylinder, r. What's the other unknown dimension here? The height. So let's call that h. So that means we want to find r and h. So let's try to get cost in terms of r and h. Okay, so the cost of the top and the bottom. The top is pi r squared. Bottom is the same, pi r squared. So 2 pi r squared. So area of the top, oops, top and bottom is 2 pi r squared. Pi r squared for the top plus pi r squared for the bottom. So the cost of the top and the bottom is what? Yeah, multiply that times 2, $2 per square meter. We have this many square meters, so the cost is 4 pi r squared. Okay, so that's the cost of the top and bottom combined. 2 pi r squared plus 2 pi r squared is 4 pi r squared. Then the cost of the sides, okay. What is the area of, I don't know if you make that a plural or not, side or sides. Okay, if you have a cylinder, here's my cylinder, and you split the side and you unroll it, what shape do you get? Rectangle. So the area outside is the area of the rectangle that you would get if you were to like split it and unroll it. Okay, so the area of the side is a rectangle, right? If you, let me go out to the side here. If you unroll the sides to get a rectangle, okay, so it would look something like this. Okay, where that is my height h. What is the length of this rectangle? Nice, yeah, it's the circumference of the circle. So the length of the rectangle is 2 pi r. So the area of the sides is 2 pi r h. That's the length times the width, or length times the height. Okay, and then it cost $1 per square meter, so its cost is the same as the area. So it also equals the cost. Okay, so if we put all that together for our cost function, it's right here, just add them all together, and we get cost C is cost of the top and bottom is 4 pi r squared plus the cost of the sides is 2 pi r h. There's my objective function with two variables, r and h. Right? I still haven't used the fact that what? The constraint? 7, right? So that's what we can use to get h. I'm trying to get h in terms of r. You want to keep going on this one? Okay. So volume is 7. Volume of a cylinder. It's the area of the base times the height. Okay, for any, what's the word? Area of the base times height. So volume is 7. Area of the base is pi r squared times the height. So let's solve that for h to get 7 over pi r squared. And I'm going to take that and bring it down for that h right there. To get cost, all in terms of r. So we'll have 4 pi r squared plus 2 pi r times h is 7 over pi r squared. Let's simplify. Simplify before we differentiate. Are there any questions so far? Okay, so my pi's cancel over here. That's nice. And one of the r's cancels. R over r squared. So if I write it in a way that makes it easy to differentiate, I'm going to write it as 4 pi r squared plus, let's write this as 14r to the minus 1. Right, so in pre-cal they might say, oh, negative exponents are bad, but to make your life easier in calculus, so that's a really fully simplified objective function right there. I would highlight it, box it, underline it, whatever. Okay. So the derivative would be, let's see, we need critical values, right? So 8 pi r to the first. Bring that negative down. We get negative 14 r to the minus 2. It won't exist if the radius is 0, but that's obviously not going to be part of the answer. So set it equal to 0 to solve for critical values. Okay, I'm going to move the 14r squared to the right and write it as a fraction as well. So I'll leave the 8 pi r on the left and write this as 14 over r squared. Okay, solve for r. So multiply both sides by r squared. We get 8 pi r cubed equals 14. So r cubed is 14 over 8 pi. That could reduce a little. What? 7 over 4 pi. So r is the cubed root of 7 over 4 pi. That's going to be the exact value. I think that's probably as far as I'm going to take it because you need to put the exact one in. So there it is, and then you can come back to h and plug in that particular r to get h in terms of r. Let me go back down. Let's use still there. Okay, so we didn't actually need a calculator at all on this one. It doesn't ask for the approximate values. So I'm hoping to find or create a problem that has nice enough numbers that you don't need a calculator in your entire exam. You've had it on your homework, so you've done enough applied problems. I feel like you're probably okay. So if I can't find one for whatever reason you really need to approximate, we'll do a 2-part test, but I'm really going to try to make it a 1-part test with no calculator. So whenever, are y'all getting my text messages before tests and things? On the Remind 101? Some of you, did you sign up for Remind 101 and you're not getting them? I don't know. Yeah. Still sign up. Okay, well, I'll put it on Canvas and Remind 101 to whether or not you need a calculator. So if I just say bring pencils and eraser, then you don't need a calculator. Did I answer your question about this problem? Okay. Do you want to work another one? It can be from anything, from the whole chapter. It doesn't have to be optimization, but optimization is fine. This is the optimization homework. Stop me if you see something. Yeah.
It's not necessarily a problem, but can you just go over quick hit points for going between graphs and stuff, like the first derivative and second derivative, like what all the critical values and everything mean, and inflection points, like just from information from like the graph without an equation. Because on the homework,
Okay.
on the homework of, I think it was the one before this.
Let's pull it up because I'm not exactly 22, 21, maybe 20. So this is 21. Is this the kind of thing you're talking about?
Kind of.
Like one of these?
Yeah.
Okay, so
Just like quick hit.
okay, so the graph is twice different from. Okay, so this is one where you have to figure out the second derivative and the first derivative and f at 1 and figure out how they're related. Okay. They're all different, all these problems are, so it's more about understanding how this needs. Okay, so like this one, f1 is, I don't know, some positive number. I know that. What's f prime of 1? Positive, negative, 0? The slope of the tangent line at 1 is negative. It's hard. So the slope of the tangent line is negative. The y value is positive. So far I know the y value f of 1 is greater than the derivative at 1. But that's all I can tell so far. Second derivative. Ooh, what is the second derivative at 1? Yeah, it's an inflection point because it goes from being concave down to being concave up. So the second derivative goes from being negative to positive. So it's roughly what at 1? 0. So I know this is negative. I know this is positive. So the second derivative must be actually in between them. So it must be like this. I don't think this is exactly what you were asking about, but like that's one example. Yeah. That was the only graph. No, there's one.
Number 14 on homework 21.
Is this 21? Yeah. So 14. Find the critical points of that and apply the second derivative test. Yeah. See that one. So this is homework 21. Oops. Homework 21, number 14. Homework 21, 14. Okay, so find the critical points, apply the second derivative test, determine whether each is a max or a min. Okay, so the first derivative, we're going to obviously have to find this first and second derivative, so let's just calculate those. So the derivative of e to the negative x, what's the derivative of e to a function? By chain rule, it is e to itself times the derivative of that inside function, so times f prime. So the derivative of e to the negative x would be e to the negative x times negative 1. I'm going to pull the negative 1 out front, write it as negative 2 e to the negative x. Okay, we can do the same thing here. The derivative of e to the negative 2x is itself e to the negative 2x times the derivative of negative 2x is negative 2. So we're going to do negative 8 times that negative 2, we'll get positive 16 e to the negative 2x. Did you follow that? Because I can write that out. Okay. So that's f prime. So we need f double prime. Same process again. Bring the negative down so we get 2 e to the negative x minus 32 e to the negative 2x. Okay, find the critical values. So we need to figure out where is that undefined and where does it equal 0. Let's write these with positive exponents. So this would be 2 over e to the x. This means 32 over e to the 2x. Are there any values of x that you can plug in that will make either of those denominators equal to 0? No, because e to the x never equals 0. So it exists everywhere, so we need to solve that equation. So I'm going to move the 32 term over to the right to get 2 over e to the x equals 32 over e to the 2x. What do I need? What's the smallest thing I need to multiply both sides by to get the x's out of the denominators, to clear those? e to the 2x, yeah. That'll be enough to clear both denominators. So I'm going to multiply both sides by e to the 2x. So on the right, they just cancel. On the left, e to the 2x divided by e to the x. There's a number of ways you could simplify that, but it simplifies to what? E to the x, yeah. There we go. So it's going to simplify on the left to 2 times e to the x. It's like e to the x squared over e to the x. One of the e to the x's cancels. Equals 32. So e to the x is 16. How do you solve that for x? Yeah, take the natural log of both sides. We'll rewrite it in exponent or logarithmic form. So we get x is equal to the natural log of 16. That's the only critical value I'm getting. Is that what y'all have? If there's not one, enter do not exist. Okay, so how do we do the second derivative test? Plug the critical values into the second derivative. So there's my second derivative, but actually here it is. No matter what you plug in, this is always going to be, well, no, it could be negative. I don't know. We're going to have to plug it in and see. Yeah. Man, I shouldn't have done that. Yeah, didn't it? Oh man, I did that wrong. Sorry guys. The solving techniques are roughly similar. I don't know why I used the second derivative test because I wasn't thinking. No, okay. Thank you. We can fix this because it's pretty similar. Okay. Let's see. So that would be negative, right? All that changes is my 32, and that should be positive. So it should be positive 16. Is that right? Negative 2 over e to the x plus... Yeah. Okay, so the multiplying by e to the 2x on both sides doesn't change. That should be negative, and this should be negative 16. So we get... Well, no, both sides are negative, so you multiply both sides by negative 1, they become positive. So this 32 becomes a 16. This 16 becomes an 8. Is that what y'all are getting to? I think so. I don't think much changed. Yay. That could have been way worse. Okay. So critical value is natural log of 8. All right, let's plug it in because this one actually involves a little bit of... that's a little bit challenging. I'm going to plug into this version of f double prime where I've written it as fractions instead of... That's not f double prime. How about that? That's f double prime. Let's just plug it in. So I want to take f double prime of the natural log of 8. This actually does simplify a lot, and you don't need a calculator for it. Plugging that in, we have 2 over e to the x, so 2 over e to the natural log of 8, minus 32 over e to the 2 times x, or 2 times natural log of 8. Is it what? What made it negative?
Oh, sorry.
Okay. I'm just trying to see if this is a positive number or a negative number. So e to the natural log of 8, that simplifies to what? 8. E and the natural log cancel. Before I can simplify this, this was kind of on your last test, I think, if I'm remembering right. You need to bring that 2 up, right? And make it, actually it's not exactly correct. Let's rewrite this. I'm going to write it bigger where you can see what I'm doing. So over here, I guess let's do this right here. So e to the 2 times natural log of 8 could be written as e to the natural log of 8 squared. Remember that power rule where the power on the log comes down out front? Notice where my parentheses are. The square is actually only on the 8, which is kind of interesting. So anyways, that simplifies because the e and the natural log base cancel. So this fraction then simplifies to 32 over 8 squared, or 64. So we have what? A fourth minus a half is negative. So all that's good that it's negative, so f is concave down, so we have a max at natural log of 8. So we have a max. Yeah, looks like there's no bearing, there's only one critical value. Okay. No, it's good. Somebody's
It's
asking.
15
Mhm.
on the same homework.
15. Hey, have you started this one? I don't know if I'm gonna have time to work this one fully out. All right, we're gonna cheat because we're short on time. I love this button. Okay, so this is their work on it. So your first derivative would look something like this with the product rule x. Okay, so they did natural log of 5x times the derivative of 2x to the 7th is that, plus 2x to the, oh, this is interesting. So they've simplified already. They're not showing all their work here. So 2x to the 7th times the derivative of the natural log of 5x. So for the derivative of the natural log of 5x, you've got P rule. So it's 1 over 5x times 5 is 1 over x. 1 over x times 2x to the 7th simplifies to 2x to the 6th. So then to solve, they factored out a 2x to the 6th. You get that. So they set each factor equal to 0. Wait, points. Oh, for x greater than 0. So I was going to say, I was looking at this one, why is 0 not a critical value? Because we set 2x to the 6th equal to 0, that's, but the domain of natural log, remember, is x strictly greater than 0. So x equals 0 is not in the picture, which might cause some people to get it wrong. So when you set this other term equal to 0, you're going to get that. Plug that into the second derivative, so you got to take the derivative of this, which they didn't, oh no, they did show here, that's the simplified version, but I'm sure you're going to get there. Plug in that crazy critical value in here, right there. They don't show what they got there, just saying it's a positive number, which means it's concave up, which means we've got a minimum. There's obviously not a lot of detail in here, so you can do your specific one if you're having much more trouble, but there's no way I can work that before we go. You have any other questions? Anything you want to look at before we go? Oh, my ops hours. I didn't put it up here. Today, I'm having ops hours today and then extra ops hours tomorrow. Actually, I'm moving my Friday ops hours to Wednesday because you're on text. So today I'll be here until 3:30. Tomorrow it'll be 1:30 to 3:30. I should be around Thursday as well, although I don't know why y'all would come. And then Friday I won't have any ops hours. Okay, good luck studying. I'll answer your questions on the discussion board, so check that. I'll see y'all Thursday.